Hey, I am Shanmukh Chowdary, pursuing BTech CSC from Bennett University. Today I am here to explain about Bell-Manford algorithm. In this video, we are going to discuss about Bell-Manford algorithm and analyze this algo and find the time complexity and discuss the advantages and drawbacks of this algorithm. History of Bell-Manford algorithm. In 1959, Alfonso Schimper suggested this algorithm. However, it was named after Richard Bellman and Lester Ford Jr., who published it in 1958 and 1956, respectively. In 1959, Edward F. Moore published a variant of this algorithm, so we often refer this algorithm as Bellman-Ford-Moore algorithm also. Leaving about the history, let's quickly jump into the topic with an example.
The problem is, in a directed weighted graph, we have to select one of the vertex as the source vertex and find the shortest path to all other vertices. For doing this, we have Dijkstra algorithm that solves the shortest path problem. But the problem here is Dijkstra algorithm will not work with negative edges. It may or may not give correct answer. So we need an algorithm which confirms that answers are correct. That is called the Bellman-Ford algorithm. Bellman-Ford algorithm uses the principle of relaxation. It follows dynamic programming. So we try all the possible solutions and pick out the best solution. So what is relaxation? If there are two vertices u comma v, if the distance of u and weight of an edge u comma v is less than the distance of v, then change the distance of vertex v to sum of the distance of u and weight of edge u comma v. This algorithm follows three steps. First step, we initialize the distance from source to all vertices as infinite and distance to the source itself as 0. And step 2 is this relaxation process. And step 3, we check whether if any negative cycle is present in the graph. Now let's take an example to get more explanation and clear. This is the directed graph. We iterate it for v minus 1 times. That is, we are having 5 vertices here. That is, we iterate here 4 times. The edges are 2 comma 5, 4 comma 2, 2 comma 4, 1 comma 2, 1 comma 3, 4 comma 3, 2 comma 3, 5 comma 4. This is the order that we are going to follow now. So let us start with 2 comma 5. If the path of this one plus weight of this edge is less than path of this one, if so, then we will change this distance. Here infinity plus 2 is not less than infinity, so there is no need of changing this. Now 4 comma 2, infinity plus 1 is not less than infinity, so there is no need of changing this one also. 2 comma 4, infinity plus 2 is not less than infinity, so don't change this. Now 1 comma 2, 0 minus 1 is less than infinity, so we change this infinity to minus 1. 1 comma 3, 0 plus 4 is less than infinity, so change this to 4. Now 4 comma 3, infinity plus 5 is not less than 4, so there is no need of changing this. 2 comma 3, this, that means minus 1 plus 3 is 2, which is less than 4, so change this to 2. 5 comma 4, infinity minus 3 is not less than infinity, so there is no need of changing this. We have successfully completed the first iteration. We are left with 3 more iterations. Let's jump into the second iteration now. We follow the same order like in the first iteration. We start with 2 comma 5, that is minus 1 plus 2 is plus 1, which is less than infinity, so we change this to plus 1. 4 comma 2, infinity plus 1 is not less than minus 1, so no need of changing this. 2 comma 4, minus 1 plus 2 equals to 1, which is less than infinity, so we change this infinity to 1. 1 comma 2, 0 minus 1 is equals to minus 1, so don't change it. 1 comma 3, 0 plus 4 is not less than 2, so don't change it. 4 comma 3, 1 plus 5 equals to 6, not less than 2, so don't change it. Now 2 comma 3, 2 comma 3, minus 1 plus 3 equals to 2, so no need of changing this. Now we have come to the last edge of the second iteration, 5 comma 4. 1 minus 3 equals to minus 2, which is less than 1, so change this to minus 2. We have successfully completed the second iteration also. After the second iteration, we can see that there are no possible changes that can be done further, like 0 minus 1 equals to minus 1 plus 2 equals to plus 1, and 1 minus 3 equals to minus 2, and 2, like there are no further changes can be done. So this is the end of the iteration 2 and 3 comma 4 also. So we have successfully completed this problem.
Advantages of Bellman-Ford algorithm. Bellman-Ford finds the shortest path between pair of vertices even if there is negative weights between the nodes. It's also simpler than the Dijkstra algorithm and more versatile. This algorithm is simple and it does not need any complex data structures and can find the minimum path weight with high efficiency and accuracy. Since it allows dynamic programming, it is guaranteed that it will generate an optimal solution using principle of optimality.
Now let's discuss the drawbacks of the Bellman-Ford algorithm. In a graph, if there is a cycle of edges and total weight of that cycle is negative, then graph cannot be solved by Bellman-Ford algorithm. We can discuss this example in the next slides. Now, the time complexity of Bellman-Ford algorithm is high when compared to Dijkstra algorithm. And Bellman-Ford algorithm deals more effectively with smaller number of nodes, not with larger number of nodes, where Dijkstra algorithm is more efficient for larger number of nodes also. But according to Bellman-Ford algorithm, after v minus 1 iteration, there shall be no further changes can be done. So for the negative weighted cycle, the Bellman-Ford algorithm fails. Now let's quickly discuss the time complexity of Bellman-Ford algorithm. The first step takes order of v time, and then for each iteration it takes order of 1 time. After v minus 1 interactions, it chooses all edges and then passes all edges to relax. Choosing all edges takes order of e time, and the function relaxation takes order of 1 time. So from this we can conclude that the time complexity is order of v into e. Considering it as n and n, we can take the time complexity of order of n square. If the graph is complete graph, that is there is an edge between every pair of vertices, so total number of edges will be n into n minus 1 by 2. So the time complexity becomes p into e, so n into n minus 1 by 2 equals to n cube. So the time complexity becomes order of n cube. So the worst time complexity of Bellman-Ford algorithm is order of n cube.
I hope I made this algorithm clear to you. Thank you for watching this video. Signing off.